So this is the last subsection of Chapter 4, and it's on model selection. Now, you're not going to be tested on this either on the written final or on the oral final. On the other hand, I think the material that's presented here will be quite helpful when you take 582 and particularly 586, so that's why I wanted to go over it. So to motivate this idea of model selection, let's consider the following. Let's say you've got a series of data that's reflected in this graph, and you've got two potential models that you could use to fit to that data. And the first one is shown by this dashed line, and it's pretty simple. It looks nice. It's nice and smooth, but it doesn't fit well. So it's not a good fit. As an alternative, you've got the solid line, which is more complicated, so it's quite complex. It looks kind of weird because it kind of goes up and down like that. That seems a bit odd, but it actually fits better. It adheres more closely to the data. So the question is, which one of these two models would you choose to fit your data? And the whole point of this subsection is to indicate that you can use the concept of likelihood to help you decide which of those two models you're going to select. So earlier on, we saw our likelihood function. Remember, this was our study where we went into Department X, we sampled n is equal to 30 individuals, found y is equal to 22 females, and then we let pi vary from 0 to 1. So this is the parameter, the proportion of females in the population. So when variable y was set at 22, and the value of pi went from 0 to 1, shown here on the x-axis. And what we can see is we could use this likelihood function to see, okay, what would be the better guess about the population parameter pi, and we say, okay, here's one guess, 0.733, there's its likelihood. Here's another guess, equal proportion of males and females, much smaller likelihood, and therefore we would say it okay. We would choose this as being the more preferable estimate for our parameter pi. And so we can do the same sort of thing when we're trying to decide which of those two models we would choose. And there's a number of specific tools that can help us with all this. And so one of the tools we've got is to calculate this value here. And it's the log of the ratio of two likelihoods. So we've got our simpler model, and we've got a complex model, and we calculate the overall likelihood of both those models. And calculation of the overall likelihood of a model is a lot more complicated than calculating the relative likelihood of two parameters, but at the same time it can be done. Now if we think about which one of these two, this one, the simpler or the more complex, is going to have the greater likelihood, well, the more complex is going to be the more likely because it fits the data better. So what we're going to have when we take the ratio, we're going to have here as a ratio a number that is less than 1. So when we take the log, we're going to get a negative number, but we multiply that by -2, we're going to return it to a positive number. So this thing all together gives us a positive number. And statisticians have been able to show that this positive number has a chi-square distribution, and we'll go over the chi-square distribution in the next chapter, with degrees of freedom equal to the number of parameters, the difference in the number of parameters, the delta, the difference between the number of parameters in the two models. So that is one tool that can be used to help you decide which of those two models is to be preferred. Another thing you can do if you've got a whole bunch of models is that you can calculate for each one something that's known as Akayaki's information criteria, and it's usually written as AIC. It's shown right there. So if we think about how this AIC is going to work, so the better model, the better fitting model is going to have the greater likelihood. However, when we multiply that by -2, the better model is going to tend to have the smaller AIC. But what we do is, after we calculate that part of the equation, we calculate this part of the equation, and we can think of this as being the penalty for having more parameters. Because P is a number of parameters. So if we go back up here to our two models, we scoot up here to our two models. So if we come up here and look at our two models, look at the solid line. It's the more complicated model. It fits the data better, so that means it's going to have a greater likelihood. But remember, after taking the log of the likelihood, you multiply by -2. So after the multiplication by -2, to multiply by -2, it's going to have the smaller value. Now, adding parameters to a model is always going to make the model fit better. So what we do, though, is we add at the end 2 times P, where P is the number of parameters. So although the more complicated model tends to have a smaller AIC because of this, this tends to offset it by adding 2P from it. So if we go back here and look at this formula for AIC, what happens is that if you had a whole bunch of models, what you can do is you can calculate the AIC for all, and choose the one with the smallest AIC. Because on the one hand, models with more parameters are going to fit better because this is going to tend to make it small, but there's going to be a penalty paid in the form of 2P for adding additional parameters. And then the last thing is, again, if we go back to our original plot, we can ask ourselves, is there some way in which we can quantify how well our particular model fits the data? Well, one way we can quantify how well our particular model fits the data is to think about the best possible model. So here would be the best possible model. And the best possible model would be arrived at just by connecting the dots. So we can get an index of how well our model fits the data by comparing it to the likelihood of our model to the best possible fit model. And so that's what we do down here in this last equation. In this last equation, we determine the overall likelihood of our model and compare it with the overall likelihood of the best possible model, in other words, the one that just connects all the dots, and that gives us an index of goodness of fit that's referred to as deviance. So again, this stuff is not going to be tested on either the oral or the written final, but I just wanted to familiarize you with some of these terms because you're going to see them in 582 and especially 586.